All right, we'll get started. So first I'll just point out that assignment 1 is out as per the course schedule. It's due February the 1st, Friday. And I just want to make sure you carefully read the collaboration policy, okay, because we will enforce it. You can work alone on this assignment, on the subsequent assignments, or you can work with one other person. That person has to be registered in the course. You have to identify them, and they have to identify you. You have to hand in separate assignments, which can be identical if you want, but hand them in separately, as described there, naming the partner. But you may not submit any solution not written by yourself. Look at any student solution who is not your official partner. This includes solutions from assignments completed in the past or previous sample solutions, and you may not share your own work with others. Okay, this is important. You may discuss your solutions with others on a high level, but you can't look at each other's assignments, you can't copy other people's answers, and so on. But you can work closely with one other person if you want to. Okay, and I think we've set up the incentives in this course to minimize cheating. So I think if you cheat, you may gain 1 mark in the assignment. You may lose 10 marks on the final exam. So your final mark will probably be lower if you cheat. So I just want to make that clear. And we will be checking, okay? Sorry to be harsh about this, but we've had problems in the past, and we don't want problems in this course. Anyway, there's lots of interesting problems on this assignment. One about putting yachts into a marina berths. What's the best way to do that? And then a couple of theoretical questions, and then an experimental question where you actually work with AI space using a variation of A star called weighted A star, where you overweight the heuristic estimate. What effect does that have? And you do explore various different situations there. Okay? So I won't talk about the assignment anymore in class unless you ask me to. There's a separate folder and discussion group set up for assignment 1 in Connect. So it's best to ask your questions there if you have any. Okay, so today we're going to look at 2 more algorithms. We're coming to the end of search. But these algorithms really improve on almost all the algorithms we've seen so far. But they put together elements of all of them. They are iterative deepening and IDS star. But first we'll review, and this is covered in the text, section 3.7.3. We'll recap from last week. I think it's important to get a big picture view of these algorithms because we've covered a fair number of them. See how they all fit together, and then motivate iterative deepening and IDS star. So we've talked about cost of search, right? So where instead of having single unit costs on the arcs, we have arbitrary positive costs almost always. And keep this arrow on there. It's better. Where the cost of a path is the sum of the costs of the arcs, obviously. We're trying to find a solution with minimized cost. We talked about what an optimal search algorithm is. When it finds a solution, it is the best one. It has the lowest path cost. It's different from complete. Complete means if there is a solution, it finds one. This says when it finds a solution, or if it does, it is the best one. Okay, you have to remember those definitions. We looked at lowest cost first. Search is one of the most recent one where you are expanding sort of a frontier out, which is basically pushing out the lowest cost path next. So the paths on the edge of the frontier are roughly equal costs. And if they aren't, then you move up the one that is of lowest costs, right? And you will eventually hit the lowest cost solution first. It's guaranteed, but it's not as efficient as A star. And of course, this is basically what Dijkstra's shortest path. How many people know what Dijkstra's shortest path algorithm is? I would think most of you do. Okay? So you obviously ask, what's the relationship between this algorithm and Dijkstra? Well, they're basically computing the same thing, except we point out some differences here, namely that Dijkstra computes the shortest path from one node to all other nodes. Of course, you could stop it when it got to the node you're interested in, but that's a difference. Basically, Dijkstra doesn't construct paths. It just works with the nodes, and for each node, it tries to compute the shortest distance to from the start. And that propagates out. It's basically marking the nodes, which can be a problem if you have very large or infinite graphs. And it does check for cycles. Okay? And if it finds a cycle, it uses the shortest path to the node on the cycle. Or if you have multiple paths to the same node, it'll use the shortest of those paths coming into the node. But it doesn't compete with A star in most applications. But Dijkstra's pretty simple, which is it's often easier to implement than some of these other algorithms. So we talked about search heuristics, which guess from any node how far it is to the goal. It's an estimate. It may or may not be an underestimate or an overestimate. If you want the guarantees that come with A star, it should be an underestimate or equal to. If it's equal to the actual cost, then A star will be most efficient. It will actually go straight to the least cost path to goal directly if there's only one path. Okay, so the closer your estimate is to the actual cost to goal from the current node, the more efficient the search. And the limit, it's ultimately efficient. It doesn't do anything but go straight to the goal. But if you just use the heuristic estimate, that's called best first search. Just using the H value, the estimate of what's to go, again using the priority queue ordered on H. It's greedy, so it can be very efficient. Again, it says here, with a perfect heuristic, it moves straight to the goal. Okay? So if it's looking at the least cost to get to the goal, it'll go straight there, if that's always estimating the best cost, and it would be perfectly efficient. But perfect heuristics are very hard to come by. And in that case, it can often get trapped, as we've seen, or it can give arbitrarily poor solutions. Okay, so it's not your best choice usually. A star expands the path with the lowest cost plus H value on the frontier, that is cost so far plus estimate of cost to go. And again, you implement this as a priority queue ordered by F now, where we call F for a path is the cost of the path to that point plus an estimate of what it costs to complete the path to goal, which we call H of P. So we use H of P or H of the node at the end of the path interchangeably because the H only depends on the node at the end of the path, so you can drop the prefix of the path. So then we talked about admissibility. We talked if C is the cost of the optimal path to any goal node, then a search heuristic is admissible if the estimate is less than or equal to the cost for all nodes. In other words, if for all nodes it's an underestimate, not strictly under, so it could be equal to the cost to any goal. And we looked at a whole variety of examples, how to build these in general, relax the problem, ignore some constraints. Just make the problem easier. If you can solve that problem exactly, an easier problem will give you a lower bound on the actual cost to solve the harder problem, right? And that's the general heuristic to construct heuristics, and we've looked at quite a few examples of that. Then we proved properties of admissibility. A star is complete, it finds a solution that one exists, and optimal. But these conditions are critical. The branching factor has to be finite. The arc costs have to be bounded below by a positive number, which is the same for all arc costs, which has to be greater than 0. And the H has to be admissible. And then if all of those conditions are true, we say A star is admissible. That's its admissibility property. So we proved both of these properties. I'll give you a different proof now for the optimality, just to sharpen your intuitions a bit, see that you can prove it in a different way. This one will be by contradiction. But the completeness proof is fairly straightforward. If there is a solution, we're postulating there's a solution, right? We're not saying there may be no solution. There is a solution. We just want to know, will A star be guaranteed to find it? It won't miss it by going off in some arbitrary direction and never coming back, right? So the way we prove that is, well, if you're postulating there's a solution that's optimal, we'll call it the cost of that optimal solution path We'll call the path S. We'll call the cost of that path F min. So this is an unknown path, but it's of finite length. And F min, therefore, is finite, because the arcs have finite costs. Okay, we proved a couple of lemmas on the prefix, any prefix PR of S. That is, a prefix of a path is a set of nodes from the start up to, but not necessarily including, the end of the path. So it's just some first set of arcs on the path S. That's PR, the prefix. Okay, so these lemmas you should be able to prove on your own. If you don't, you should try and figure out why. Okay, so these are little lemmas, little theorems we're going to prove about this prefix. Okay, the first lemma is that the cost, the F of PR is less than F min, where F is the cost so far plus the estimate to go, right? That's less than or equal to F min. That's obvious because this includes an estimate of how far to go, and that's less than the actual cost, whereas when we actually get to the end of the path, S, we've got F min, which is the true cost to get where we are. Whereas for the prefix, we estimated that cost, but we did it with an underestimate, okay? So the cost of the F value for the prefix must be less than or equal to F min. That's because of the admissibility property. And we will prove that there is always one such prefix on the frontier, waiting on the frontier to be expanded. There's always one there until it terminates. You can prove that by induction. Initially, there's one such thing on the frontier. That's the start node, right? And every time you expand a node, there will always remain one prefix on the frontier. So if we have those two properties, then we can prove our theorem. We show that A star will only expand paths with F of P less than or equal to F min. So it expands paths P with minimal FP. That's how A star works, right? There's always a PR on the frontier with the F value of that prefix less than or equal to min, which we've proven up here. And it terminates when expanding S. One thing we have to do, though, in this proof is to show that there's a finite number of paths whose cost is less than or equal to F min. Okay, otherwise, you could imagine that if there were an infinite number of paths who were cheaper than F min, you'd be constantly expanding those before you get to the minimal cost path. And that's the critical reason for having the cost of an arc bounded below by epsilon. Okay, if that's true, you can never get an infinite number of paths cheaper than F min. And that's what we do here in this section of the proof. We'll let C min, we called it epsilon before, we're now calling it C min for minimum cost. That's the minimal cost of any arc. We'll let the number K be F min, which we know exists as a finite number, real. C min's a finite real. By one by the other. This is probably close to an integer. Let's round it to the nearest integer, up. Then all paths with length greater than K have cost greater than F min. Why is that true? Well, every arc costs at least C min, right? So if you have more than K of them, the total cost of that path is greater than F min because of the way we constructed K. Just think about that, draw it out, you see it. So there are only a finite number of paths of length K. There are B to the K. The branching factor is B. At level 1 you have B. At level 2 you have B squared. At level K you have B to the K paths. Okay, that's a finite number. Because B is finite. That's why we have to have a finite branching ratio. That gives this as a finite number of paths whose cost is less than F min. So we keep expanding paths as long as their F value is less than F min. There's always a path on the optimal path whose cost is less than or equal to F min. And so we will expand that path before we go on and expand any paths whose cost is greater. There's a finite number of paths that are cheaper than F min, so we've eventually got to get to the optimal path. Okay? Is that okay? It's in the book. You don't get it, but I think I've explained it. Make sense? Any questions? That's just proving that it halts. If there's a solution, it'll halt. And it'll halt with the cheapest possible solution. That's the next part, is the cheapest possible part. Okay. Why is it admissible optimal? So what's the optimality property? That it finds the cheapest solution first. The first part, we just showed that it found a solution. Now we're going to show that it's the best. And so you could use the direct proof that I gave you last week, or you could use this contradictory proof by contradiction. Let's assume that it's false. We assume the hypothesis for contradiction. We hope to contradict the hypothesis, show that this leads to a contradiction, so the hypothesis can't be true. Standard logic. Let's suppose that the first solution, S prime, that A star expands is suboptimal. Right? So it expands a non-shortest path. So that the definition of that is the cost of that path is greater than F min. Okay? Since S prime is a goal, that's a solution at the end of S prime, the estimate H of S prime must be equal to 0. Why? Because the estimate must be less than or equal to the cost to any goal. And the cost to a goal is 0, so H of S prime must be 0. And F of S prime, which is the cost of S prime plus H of S prime, which is 0, is equal to cost of S prime. So F of S prime must be greater than F min. A star selected S prime. That must mean that all other paths P on the frontier had F of P, their F cost greater than equal to F of S prime, because the way A star works is it picks the path with the lowest value of F, right? And we know that F of S prime is greater than F min, which we proved up here, right? So we have F of P greater than or equal to F of S prime greater than F min. But from the previous proof, we know that a prefix PR of optimal solution path S is on the frontier with F, the F value of that PR, that path, the partial path, is less than or equal to F min, right? So we have F of P here is greater than F min, and that's the one selected, but there's a path waiting on the frontier with its F value less than F min. So A star has not done the right thing. It hasn't picked off the cheapest path, so that's a contradiction. So this hypothesis must be false. So that means the first solution, S prime expands, is optimal where the cost of that path is equal to F min. Okay, so that's a proof by contradiction. It's useful to prove things more than one way. The summary of this proof is simply that any prefix of an optimal solution is expanded before any suboptimal solution would be expanded. Remember, expanded is when we check for the goal property. If we checked it when we generated the node, this theorem would be false. Okay, so we have to leave a potential goal path on the frontier until we pull it off and look at it and say, oh yeah, that's a goal. Now I will stop. Okay? That's what gives us the optimality property because of how we proved it here. Okay? Any questions about that? No? You hate proofs? Get the sense there's a little hostility towards these proofs. You just want to go out there and code, right? Okay, so that is all really the last 17 minutes have just been review of last week. So this is what we did. Looked about selecting the most appropriate algorithms. Depth first, breadth first, least cost, best first versus A star. You can define, read, write, trace, debug those algorithms with or without cost, informed, uninformed, you know what that means. You know how to construct heuristic functions. You can formally prove these theorems that A star is complete and optimal. And we defined optimal efficiency, which means that if we have two heuristics and one is greater than the other, but they're both less than the true cost to goal, the one that is greater will give you a more efficient search in the computation, although both will give you exactly the same path to be executed. Okay, do you understand that distinction? So it's good to summarize all of these results because we've got a lot of them in a table, and that'll motivate the next part of this lecture. So we've got all these algorithms. we just talked about. We've got completeness properties, optimality properties, time and space complexity results. And notice in the complexity, everything is exponential except this one, linear space, both in the depth of the search and the branching ratio for depth first search. However, the price you pay as depth first search is not complete, especially if there are cycles or if it's an infinite graph. But if the graph is finite with no cycles, depth first search is complete. But it's still not optimal, because it might find a very deep solution on the left-hand side of the tree before a very shallow one on the right-hand side, right? Whereas the optimality results come with BFS, LCFS, least cost, and A star. No optimality with depth first because it's too optimistic in a way. It's searching too hard. So, that's interesting. We can't have our cake and eat it too. You can't have optimality, completeness, and linear space in the same algorithm yet. We'll get it. You can never get exponential time unless p is equal to np, and you'd be worth $1 million if you could prove p is equal to np. In other words, that these np hard problems can be solved in polynomial time. If we get a polynomial time bound for any of these, if I have one of those, I wouldn't tell you about it. I'd just submit it to the prize committee and get the $1 million. So, exponential time is not going to happen probably, but the problem with exponential space is if you have exponential space, you're guaranteed to have exponential time because you've got to look and maintain all that space, generate it and check it and so on. So we really want to get better on the space department without giving up optimality and completeness. And that's what this algorithm iterative deepening does. So what we want, the motivation for iterative deepening, depth first search, instead of saying IDDDFS, we say IDS. We want low space complexity but maintaining completeness and optimality. So we want to have our cake and eat it too, and we can do that, turns out. A really neat idea. It's very simple. You may have encountered it. Who's encountered iterative deepening before? Okay, so this is new for all of you. It's amazing because it's such a beautifully simple and powerful algorithm. Very simple idea. Don't let depth first search run away. Okay? We're essentially going to simulate breadth first search, but without the space costs. That's one way of thinking about it. So there are two ways of thinking about this. One is we're not going to let depth first search run away because we're going to put a depth bound on it and back up whenever we get to the depth bound and slowly increase the depth bound. But the effect of that is to kind of simulate breadth first search. Okay? So you simply, in the outer loop, you run depth first search, but you wrap an outside loop around that which just bumps up the depth counter by 1 each time. So you start with the depth of 1, then 2, then 3, and so on. Allow it to go to the depth bound. And if you haven't found a solution, then back all the way out, forget everything you learned, and do it again 1 more level deep. Okay? Which seems dumb in some sense because you're redoing all that work. But as we'll find out, it's very cheap to redo all that work, and it gives you huge benefits. Okay, so this is what it looks like. Here's the loop counter. Depth is 1. This means we go down to the first level. And if we haven't found a solution then, you fail out and increase the depth bound to 2. And again, look at all the same nodes, except we go 1 level deeper. Okay, this is depth first search. And basically what we're doing is simulating a failure. Whenever we reach the depth bound of 2 here, we'll simulate a failure here. If you haven't found a goal, and say, can't go any further, fail back, try the other option. Go up there, try that, try that, try that. And eventually, you'll explore the entire tree down to depth of 2. And then you do the same thing down to level 3. And you can see, depth first search you can just implement with a recursive function. It's the first thing. And then you just wrap that recursive function call in a simple iteration, increasing the depth bound each time until you find a solution or until you run out of time or patience or whatever. So you probably have to set a max depth bound if there's no, just in case there's no solution. So the claim is that this isn't as wasteful as it sounds, and in order to do that, we'll have to do a little algebra to prove it. So we're looking at the time complexity of iterative deepening search. Now, it seems dumb to repeat. You know, every time you fail out, you just forget you ever did any searching. You don't learn anything. You keep looking for goals at lower level, you know, at higher levels in the tree you've already looked at. You just look at them again. Okay? So it's completely without memory, this search. So what we want to look at is the total number of paths that iterative deepening search generates. That's our measure of complexity for all these algorithms. How many paths does it generate? How much space does it use? So on the first iteration, there are B paths. There are branching factors B. So at level 1, there are B different paths. And these are the number of times this path will be created by breadth first search or by depth first search. They all only do it once, okay? They'll be true all the way down. But at depth 2, there are B squared paths. And down at level M, there are B to the M paths, right? We know that already. So now we're going to look at what iterative deepening search does. So at level 1, it repeats that M times, right? Because we're going to increase the depth counter from 1 to 2 to 3 up to M. So we're going to look at that first level M times. Look at it each time we iterate through that loop. Right? So there's the repetition. Instead of depth first search just looking at it once, we're going to look at it M times. The next level down, it'll be one less number of times we look at it. Right? Until right at the bottom, you only look at the leaf nodes if the maximum depth is M once. Right? Does that make sense? So now, we want to multiply. In order to look at the total number of paths IDS looks at, we have to multiply the total number of paths at each level by the number of times that's created. Okay? So MB, M minus 1 B squared, and so on. Right? All the way down to B to the M, which is a large number. But it's the same number that depth first search or breadth first search will look at. The key is, of course, that this number is going to dominate. And the fact that we look at these guys a whole bunch of other times isn't so important. We can see exactly how important it is. But basically, that's going to dominate. And it's the same as before. But we're doing this with linear space. Right? The total amount of space we're using is always the same. It's always depth first, which really just has one path. So the total space used is B times M still. Right? And we're just looking at the time complexity. We're looking at the total number of paths generated here because it costs you every time you generate a path. And we're regenerating all these paths at the higher levels in the tree very, very frequently. But the fact is the number of paths down here will dominate all those numbers. Okay? So we can prove that, a little algebra. So we're looking at a solution. Suppose there is a solution at depth M with a branching factor of B. The total number of paths generated is just summing up that right-hand side column that we had here. Summing that up is B to the M plus 2, B to the M minus 1 plus 3. You know, it's a funny arithmetic geometric series, combination of the two, right? Not clear how to get a closed form for that, which is what we want. In fact, there is no closed form solution to sum this series, but we can get an approximation to it. What we're going to do is take out the B to the M here, because then this thing will be decreasing. B is some integer. So these terms will be all integers. And as I said, this term is going to dominate, right? So we say, well, it's B to the M times some factor. And we're hoping that's small, like less than 3 or 10 or 2 or something, right? If that's the case, then we had B to the M time complexity before. We still got B to the M time complexity. We haven't made the time complexity much worse. The space complexity has improved enormously. So here's the algebraic juggling. We're summing this series, which is the sum as I goes from 1 to M, I times B to the 1 minus I. That's just rewriting this term here, right? And we can actually rewrite this. So b is an integer. 1 over b is less than 1. So we'd like to use b minus 1 here. This is exactly the same. There's no jiggery-pokery. This is just 1 minus I is minus 1 times I minus 1, right? Except this will be now less than 1. It'll be decreasing, which is what we want. And that's the sum from 1 to m. This is where we do an approximation. For this kind of finite series, there often isn't an analytic solution, but if you make it infinite, there is. So let's just bump the bound from m to infinity. Could only make it worse, so let's not worry about that too much till we see how bad it is. Okay, so this, the actual number of paths generated, the time complexity, is less than or equal to this quantity. Looks like we made it worse rather than better, but here's a little fact you may or may not know. I don't know if you remember your calculus, how to expand 1 over 1 minus r using a Taylor series expansion or something like that. But you can look these things up in tables, right? 1 over 1 minus r is the sum, if r is less than 1, absolute value less than 1, is an infinite sum of 1 plus 1 over r plus 1 over r squared plus 1 over r cubed. That's equal to that. Okay? It's easy to prove with simple calculus. Even better, we can show that if you differentiate this formula here with respect to r, then if you differentiate that with respect to r, you get r times r minus 1, right? That's calculus. Taking the derivative inside the sum, which is legal. And so I differentiate the left-hand side with respect to r and the right-hand side with respect to r, right? Derivative of that is 1 over 1 minus r squared. And that's looking kind of interesting. It's looking close to what we want here, where r is 1 over b, right? So we can actually get a closed form solution there for this upper bound on the time complexity. So we kept the m to the outside, and here's the factor by which b to the m increases. This will be greater than 1, and then you square it. So the factor is just b over b minus 1 squared. That's an upper bound, because we went from here to something bigger. So b might be, b is 3, then that's 3 over 2, 1.5 squared, 2.25. That's the additional amount of work we have to do, just over twice as much work for b equals 3. B is larger, it'll be larger, but it's a constant factor. So we can drop it in the big O terminology, right? So, still order b to the n. So, got your cards. We're interested in the space complexity of iterative deepening. If I didn't put you to sleep with the analysis of that algebra, you heard me say the answer to this question. If you forgot your cards, you can always get more over there. If you don't have your card up, is it because you don't have it? You don't want to put your answer up? You don't know what the answer is? You should know the answer to this. At any point in the iterative deepening search, there is only one path active, because it's the same as depth first search. There's only one path active coming down wherever it is. There's only one path active at a time. So you only need that much space. You can reuse that space over and over again. There are lots and lots of paths generated, b to the n paths, but there's only one at a time. So there's no bulge as you get with breadth first search or anything else. The space complexity is order bn, still, as it was for depth first search. Okay, so it's the green one. You're only exploring one branch at a time. Is iterative deepening depth first search complete? Let's assume that the arc costs are 1, just for the sake of argument. If there is a solution, will it find it? Yes. Most of you got that. Because it can't shoot on by. It's very conservative. As you see, it's almost like breadth first. First it explores at level 1, then it explores at level 2, then it explores at level 3. We're simulating breadth first search and depth first search without the overhead of the space required. So it gets breadth first search's property, which is that it's complete. Is it optimal? Suppose there are costs of only 1 for now, as we did. Yes, it's optimal again, because again it inherits that property. And you could easily prove it by contradiction if you were asked to do so in, say, I don't know, an exam. Okay? I mean, but it's clear, because again it's like breadth first. It's so conservative, it's just stepping down the levels. And it's, nobody could sneak by it, and you're going to find the cheapest solution first. So we now have iterative deepening search here. It's complete, it's optimal, it has the same time complexities. I say that's probably a given. We probably can't do better than that because of P not being equal to NP. But the space complexity is now as good as depth first search, but it's, instead of being not complete and not optimal, it is complete and it is optimal. And the beauty is it's so simple to implement. Okay, so we can go even further than that. It's amazing, actually. This took a long time to pop up in the literature. That you could do the same thing with A star, with non-uniform costs. So, we've been assuming single unit costs for the arcs for iterative deepening search. But imagine doing the same thing for A star now. But instead of using the depth bound, we could use the F values. Okay? So start with some low value of F and just run iterative deepening depth first search. But instead of cutting off at a depth bound, cut off at an F value. You know the F values for all the nodes. They're cheap to compute, right? So as soon as you get to nodes that are beyond the depth bound, say I'm not going to go there. I'm just going to keep looking at the other nodes that I haven't yet expanded that have an F value less than my F bound. Okay? If you've exhausted those and you still haven't found a solution, what should F jump to next? What should your next F bound be? It should be equal to the F value of the node that you didn't look at that was closest to the F value. In other words, if my F value is 20, I look at all nodes with F values of 20, I don't find a goal. But I try to look at nodes with F values of 23, 27, 30. I'd use F as 23 as the next cutoff. There might be more than one. I'd look at everyone at that level. But still just running iterative deepening search on it. Okay? And each time I exhaust and I don't find a solution, I bump it up a little bit more. You can see that this has the same properties as A star, except that it doesn't have this gigantic frontier which explodes on you with A star. Okay? So iterative deepening A star is a very pretty little extension of iterative deepening that would be more efficient because you're not managing all that space, and it's actually simpler to implement because you don't have to manage that frontier as a queue and so on. And it has the same properties as A star. Okay, I think this was invented in the 1980s. I mean, it was 20 years after. Well, iterative deepening came first, had to come first, but then someone realized, oh, was Cork who invented this. Does that make sense? You see how it implements A star in a very simple way, and it's more space efficient. So again, is it complete and optimal with the same conditions as A star? H has to be admissible. All the arc costs have to be greater than epsilon, greater than 0, has to be a finite branching factor. If that's the case, then yes, IDA star is complete and optimal. What's the time complexity? Well, same as before. Big. We're stuck with that. What's the space complexity of IDA star? Okay, about half of you are awake. That's not bad. Yeah, it's linear. It's just ID. It's iterative deepening search. We've already seen that iterative deepening. The only change, the only thing we did, it looked like sleight of hand, the only thing we did was instead of using the depth bound to cut off the search if you don't find a goal, we use F values. We start them out really small and then increase them. We always increase them to the next node, the F value of the next node that got cut off in the previous go-around. And there'll be a finite number of those, and they will increase in systematic ways until eventually it'll be equal to the F value of the actual goal. Okay? Same argument. Okay, so now we've completed our chart, and we have IDA star, which is now complete with the same conditions as A star. It's optimal. It has still exponential time, as they all do, but it does get us back to linear space again. And just as with IDS, you can show that the overhead of IDA star isn't that great. It's harder to prove analytically. We won't prove it. You don't have to worry about it. And in practice, because it's simpler to implement and you're administering less space, it can often be much faster than A star. Although the worst case is still the worst case. They're all exponential. Okay? So, what have we learned? We've learned about iterative deepening. We've gone over ad nauseum the properties of A star and all the other algorithms. We know all the properties, and we know that table cold of all the basic properties of all these search algorithms, the completeness, optimality, time and space complexity issues. So, do the practice exercises. They're there for your entertainment and your joy. Assignment 1 is there. Do it. And we're done. Thank you.